linear transformation, or you can also call it a linear map, right? So linear. Linear transformation or linear map. I'm sure this one you did a bit of it, and linear algebra. Okay, second year. Okay, yeah. So let's write. So definition. Definition. Good. Definition. Definition. Let X and Y be a linear space. So let X and Y be linear or vector space defined over the scalar field F. Over the scalar field F. Over the scalar field F. A mapping. A mapping T from X to Y. Right. In that the linear or vector spaces are X and Y. So the map takes an element from the X, is acting as the domain to what? The codomain or to Y. Good. So this mapping, this is said to be linear if the following conditions holds. Okay, so we realize this one is also a condition. That satisfies some condition before we can call it what? A linear map or linear transformation. So the first one is this one. You expect that the T is representing the transformation, right? The transformation. T of, let's say, x1 plus x2. Remember, x1, x2, they are members of the vector space X. Okay, so pardon me if I'm writing the x1 in this form, right? We can write this as T of x1 plus T of x2, of course, comma, for every x1, comma, x2, a member of capital X. The second condition, T of alpha X is equals alpha Tx. Of course, for every X member of capital X, and alpha is a scalar. That's a member of the field F. Okay, good. So if a space or if a map satisfies, yeah, it's a mapping, right? If the map satisfies these conditions, two conditions, then you call that map what? A linear map or a linear transformation. Okay. So if I have to justify that a map is a linear map, you can go by these two. Okay. Good. But at a point, you can combine these two as one. Okay, so that you are justifying only once. Okay, and I usually prefer that one. Combine these two and then use it only once. Good. Let me call it a mark. Mark. Good. So realize that the two conditions above the two conditions above, can be combined. The two conditions above can be combined to get a single condition. The two conditions can be combined to get a single condition. That is for every x1 comma x2 a member of capital X and alpha beta, they are the scalars, right? Let the scalar be what alpha and beta. So, comma C of alpha x1 plus beta x2. This is equals, you can write this as alpha out C x1 beta C x2. So instead of alpha beta, somebody can say alpha 1, alpha 2 as scalars. Okay, good. So let me call this as one, the first remark, second remark. Second remark says this: if x is equals to y, comma, then becomes, if x equals to y, realize that t of x, t taking an element from x to y, now becomes what? T of x to x. And t is called a linear operator. So if x equals to y, then you don't call it a linear map or linear transformation, you call it a linear operator. Okay. Call it a linear operator. Are you okay? Examples. Let's got some few examples. So examples. Good. The first one says this. Let me write one. So if x and y are vector spaces, of course, over F. So that our field we call it F. Then the map C from X to Y defined by T of X equals 0, comma, for every X a member of capital X. Is a linear map called the zero transformation. So call it the zero transformation. So call this for the zero transformation. Well, so let's justify it. We want to justify that t of x equals 0, or t of x, or the map t is what? A linear transformation or linear map. Linear transformation or linear map. So to justify that it's a linear map for sure, if you want to use the combination of the two definitions, then you have to get what? Your scalars, you have to get what? Two elements. The x1 is with their vectors, right? So you have to get that one from the space x. So what do you want to do? You want to show that t of, let's say, alpha x1 beta x2 is equals to alpha out so that's what we want to justify. So we need the two vectors. So say this for every x1 comma x2 a member of x, and you can say scalars alpha beta. So you always make some argument on the definition. The definition is what t of x is always equal to 0. Okay, t of whatever is 0. That's what it's saying. Good. So we are starting from the left hand side here. We want to arrive at this. Okay. Okay. Good. So this means that t of alpha x1 plus beta x2 will be equal to what? How we agree? It's equal to 0. Equal to 0. How we agree? When you agree that 0 is the same as alpha times 0, beta times 0. How that one agree? So the dot here means times. And remember, the definition is reversible. T of x is equals to 0. 0 equals to t of x. So we are saying the t of anything is 0. How we get it? So this one for sure, this can be that this 0 here is the same as t of x1. This 0 here can also be t of what? x2. So you have achieved that. Once you're able to write this as that, you are done. It's a linear transformation. Right? So therefore, T is a linear map, or you can say it's what? A linear transformation. It's a linear map or linear transformation. Because T of whatever is still 0. So you can rewrite this as that. It's true. Example 2. Example 2. Example 2. Let's pick this one as an example 2. Select a mapping T of x to x, right? Be defined by T of x equals what? X. Of course, comma for every x a member of capital X. Full stop. Then T is a linear map called the identity map. Identity map, right? Because T of x is given as the x back. Okay. So term it as what? The identity of map. Identity map. Identity map. I remember into analysis, it proved something like that. It showed that the identity function is continuous, if you recall. Yeah. F of x equals x. If it's an identity map, then you say it is what? Continuous. Remember, we justify that. Yeah. And it's called a linear operator. Yeah, I can also call it a linear operator. That's what you mean. Yeah. Okay. It's a linear operator though, but we want to justify that if it's that linear operator is a linear map, then you have to satisfy the condition of the linear map. Okay. Good. So proof. Good. So by the conditions, we need what? Two elements from the space, and we need two scalars. Okay. Good. So say that for every x1, comma x2, a member of x, and scalars, sorry, alpha, beta, T of alpha x1, beta x2 should be equals to. Now we come to definition. What the definition says? It says T of whatever is still what? Whatever is there. Okay. So like T of 5 will be 5. T of whatever is here is here. So T of this will be equals what? Alpha x1, beta what? x2. Hope that's true. Okay. As you are done. You are done. As I said, the reverse is also holds. T of x equals x means x is equals to T of x. So what will be x1? X1 will be what? T of S2 will be what? T of S2. And you are done. Okay. So this means that T of x1, T of x, sorry, x is what? T of x1. This is what T of x2. Once you're able to write this as that, that means the T is what? A linear map for that. Very simple as that. See that the definition is very important. So I said pure math definitions are very key. Can't leave the definition out. Are you okay? So look at the third example very soon. Okay. Good. A third example. Good. Sorry. Example 3. Let T okay, two-dimensional to what? Two-dimensional be defined by T of x comma y. We are saying this equals to x comma negative y. For every x comma y a member of R. So that T is a linear transformation. In fact, this one is called reflection in the x-axis. You can see that. This is called reflection in the x-axis. Reflection in the what? X-axis. So see, look at this. Look at the domain. Always pick the elements from the domain. The domain, as you can see, is a plane, X and Y plane. So this time we can't pick the members as just vectors like that. It should be in pairs. X and Y plane. Okay, so we have to pick the element as pairs. Okay, let's say x1, y1 as one pair, then x2, y2 as one pair. Okay, good. If we're just R, then it will be x1, y1. Yeah, okay. Okay, so by in this case, if it's Q, how to be x1, y1, z1, something like that. Okay. So be mindful of that, yeah. Because that's it, because you see that it's defined in pairs. Reflection the x-axis. Okay. So want to show that this one is what a linear map. Okay. So that is a linear map. So the same preamble, the proof, so that for every x1, y1, comma, x2, y2, a member of what? R square. Of course, there are scalars, right? And scalars, alpha, beta. So look at the definition. T of xy is equals to what? X, then the negative what? Y. So you negate the second component. Good. Negate the second component. So this as I said, they are in pairs. So this means that T of, let me put in this way, right? Alpha x1, y1 plus beta x2 y2, right? So it's going to be x1 x2. We say that t of alpha x1 plus beta x2, right? But this one in pairs. So this one is equals what? So first of all, you can simplify it to be in the form of this before applying the definition. So to apply the definition, there should be x aside, y aside. Then good. So first of all, let's expand it. This is t. We agree this is t of alpha x1, comma alpha y1, isn't it? Plus b x2, comma b y2. Oh, that's true. Next, you put the x aside and the y aside. So this one will be t of alpha x1 plus beta x2, isn't it? Comma, okay, alpha y1 plus beta y2. So now you have separated them, the s aside, y aside. So once s is aside and y is aside, you can now apply the definition here. The definition says what? Keep the first component but negate the second what component. Apply the definition. So this will be equals to, without the t, right? This will be alpha x1 beta x2, but minus, comma, minus that. So you see that's negative by definition. That's true. Okay. Remember, I want to achieve that this is equals to what? Alpha out t of the first component plus beta out t of this one. So that's what I want to achieve. Good. So next, let's put all the y1 aside because we want to achieve this x1 y1 at one part, 1 point, x2 y2, another point. Okay, achieve this s1 y1 at 1 point. So let's separate the ones aside and the twos aside. That's what I'm saying. Good. So you realize that by so doing, this would be into bracket alpha x1, right, comma negative alpha y1, then plus the betas beta x2, comma negative beta y2. That's one grade. That's true. Good. Good. So this will be equals to really write that. This implies this equals to, now see, can factorize alpha out, the other part can factorize beta out. So alpha out, then we left what? X1 negative what? Y1 plus beta out, left what? S2 Y2. Definition. Back to definition. So you can reverse. If T of xy is equal to x negative y, you realize that x negative y is T of xy. Okay. So you can reverse this. You can also reverse this. This is alpha. This is T of x1 y1 beta T of s2 y2. So whenever we have this, can write it this way. Have this, can write it this way. To have this. Okay. So you see that we have achieved the definition of what? Or the conditions of a linear transformation. Whenever you have this, you can write written as what? Alpha out. That. Okay. So hence T is what? A linear transformation. So hence T is a linear transformation. T is a linear transformation. Good. Good. So let me give you some for you to try later. Right. Hope it's okay, it's clear. Good. So try. Let me give you something to try. Can I clear the board? Good. The trial exercises. First one is this. Very simple. Select T R to R be defined by T of x, let's say equals to 3 plus 2x. For every x a member of R. All right. Verify whether or not T is a linear map. 2. Since it's determine whether or not each of the transformation below is linear. That means I want to just find this a linear transformation. T defined as this R cube to what? R cube. Defined by, so the first one I want to just find a T of x, y, z is equals to 1 z. Of course, command for every x, y, z, a member of R. Okay. No, just try exercise. Yeah, you try later, right? Next, T of x, y, z is equals to x, y, comma for every x, y, z. Okay. I. We say this we have this already. Yeah, so this T of R squared. So this is 3, sorry. So let me call this one 3. Oh, that's the third one. Because it's a different definition. 3. Okay, here you have been given the mapping as this. Defined by T of x by I squared. X. Okay. So it's enough. Let's move on to something else. So, you can try hands on that. Good. Next, you look at what you call standard matrices. Standard matrix. Definition: standard matrices. called a standard matrix. You're writing. So the standard matrix of a linear transformation T of R n maps to Rm has columns T of E1, T of E2 up to comma T of En. So it's a matrix. When I say that the columns are what? T of E1, T of E2 up to T of what? En. Okay. Where E1, comma E2, comma up to comma En represents the standard basis vectors, standard basis vectors in Rn. That is T of x is equals Ax. So this implies that A is a matrix, right? We are saying that the columns of this matrix A are Te1, comma Te2, comma up to comma Ten. So this is a matrix. You could say that E1, E2, En they are standard basis. So what are they? Did this one in algebra, right? That's a linear algebra. Standard basis, what are they? U1 represent what? What are the standard basis? They are standard. You have U1, U2, U3. It depends on how you want to represent it. U1 represent what? U2 represent what? U3 represent what? They are more they are column vectors. Okay. So if you say U1, U1 means that U1 means that the first entry is 1, the rest is zeros. U2 means the second entry is 0. So it's 1, the rest are zeros. How we get it? U3 is more like U3 will be what? The third one will be what? 1, the rest zeros. U4 means the fourth one is what? 1, the rest zeros. Okay, good. So more or less, so U1 is 1, assume it's 2 by 2. U2 will be what? 0, 1. U3, 0, 0. U4, 0, 0, 0. The fourth one is what? 1. We call this a standard what basis. Yeah, standard basis. Okay. Yeah. So the one there represents the position of the one. First one. The 2 here means that the position of the one is at the second. U3, the position of the one is at the third. Like that. Okay. We term them as what? Standard what? Basis. Standard basis. Standard basis. As we move forward, you define what you mean by basis. By basis. by basis. So when do you say, assume we have 2 or 3 vectors, when do you say they form basis? The vectors form what? Basis, right? So if you say vectors they form basis, it means this. First of all, the vectors they should be linearly independent. That's one condition for basis. Second, if you pick any vector, you should be able to express the rest of the vectors as a linear combination of that. Okay, so as we have E1, E2, E3, I said they are basis. It means that first of all, E1, E2, E3, they should be linearly independent. Okay. 2. If I pick, let's say U1, U1 should be able to express as, let's say, alpha E2 plus beta E3. That means they are linearly combination, right? U1 can be written as a linear combination of the rest. If you pick U2, so you're able to write U2 as a linear combination of the rest. U1 and E3. That's it. Okay. So once you satisfy these two conditions, then you say the vectors are what? They form basis. Okay. Good. For example, let's take an example for you to get the clear concept of it. Good. Find the standard base, the standard matrix for, so example, so this, find the standard matrix for the transformation T, where T of x1, x2, x3 is equals to x1 minus x2 twice x3. Okay, good. So it's a map. You see that the elements here, 3-dimensional to what? 2-dimensional. How do you see that? 3-dimensional, right? To what? 2-dimensional. Okay. So let's look at the solution to it. We want to find what? The standard matrix. Okay, good. We say that the standard matrix here, the columns are the T of what? The standard basis. U1 here. Solution. You are writing the above means that T RQ to what? R2. Okay. So you are moving from 3-dimensional to what? 2-dimensional. Right. And that means the matrix that we are looking for must be a 2-by-3 matrix with columns, namely, right? Good. So what is this? See that in the note we wrote what? N M. Okay. By usual matrix is M by N. Okay. M by N matrix. Okay. That's why we say the matrix should be what? 2-by-3 what matrix. Right? 2-by-3 matrices. Yeah. row column, 2 rows, 3 columns, right? Namely, we are looking for what? I mean, we are looking for must. So the metric you are looking for, that means the matrix that, right? We are looking for must be a 2 by 3 matrix with columns. Yeah. We said the columns are T of U1, T of U2. So 2 by 3, that means the columns are 3, isn't it? Good. And T of U3. 1, 2, 3 columns. 1, 2, 3. Where where U1, U2, of course, U3, they are a member of the domain. Okay. That means the U1, U2, U3, they are supposed to be in 3-dimensional cases, right? Good. That is, so what will be U1? So if U1, U2, U3 are coming from a 3-dimensional space, so how do you write U1, U2, U3? Okay. So you realize that U1 will be equal to 1, 0, 0, isn't it? U2 will be what? 0, 1, 0. And of course, U3 will be what? 0, 0, 1. The third position will be 1. These are the columns of that. Now back to definition. Definition says what? It says a T of x, y, z is equals to what? What was it? X1 minus what? X2 twice x3. We are going to use the definition to get the T's of U1 and U2. So what will be T of this? T of U1 will be equals to T of, that's why we have this first bracket. What is U1? U1 is what? 1, 0, 0. What are the definition says? Remember, this will be your x, y, z. Okay? Yes. So we are looking for U1. So what will be U1? U of t 0, 0. We are using this definition. Remember, as I said, this is what? X, y, z. Right? No. It's the other one. X2, sorry. X1, X2, X3. So that to satisfy that. Okay. Sorry for that. Okay. Good. So that's X1, S2, S3, right? Good. Good. S1, S2, S3. So what will be the definition? So the first component is what? S1 minus S2. So what will be x1 minus s2? X1 minus s2 give us negative what? S1 is 1, right? 1, good. The next component is what? Twice that. So it's what? 0. So this is our T1. That means our first column will be 1, 0. We move on to what? Yeah, TU2. T of E2. That will be T of, what is E2? E2 is 1, 0, 1, 0. By definition, the first component is what? X1, X2. That will be negative 1. Twice the third one, 0. Okay. Lastly, look for E3. That will be T of E3 is 0, 0, 1. Definition, x1 minus what? x2. So that will be 0. Twice the third one, that will be what? 2. Okay. And you say that T1, T of U1, T of U2, T of U3, they are the columns of the standard matrix. Okay? They are the columns. So when you go and face them as the columns, then you have your 2 by 3 matrix. You are done. You see this very straightforward there during this time. So we are saying that, so this implies that your T, that's the standard matrix, is A, right? We call it A. Find the standard matrix, right? That's what this question says. This implies a standard matrix. Can you see that? Standard matrix A is equals to the columns is this, right? T of U1, T of U2, T of U3. So that's T of U1. T of U1, you had what? 1, 0, 1, 0. T of U2, you had negative 1, 0. T of U3, you have 1, 0, 2. And this will be, it's a 2 by 3 matrix. Yeah. That's our standard matrix. Yeah. Well, as a standard matrix for T, right? A standard matrix for the given transformation. T is that. Okay. Pass. Are you here? Good. Good. Another example. Good. Says it's given that T R Q R Q. It's a linear operator. So the domain is same as the codomain, right? Call it the linear operator. Linear operator that maps 1, 0, 0, 2, 1, 2, 3, 0, 1, 0, 2, negative 1, 1, 1, 0, 0, 1, 2, 1, negative 2, 0. So look at the left hand side. Well, like this one is the U1, U2, U3. Yeah. Comma. comma, says what? Find the standard matrix T and use it to determine T of 3, 4, -5. Good. Solution. Right. So first of all, we get the standard matrix, then use it to what? Determine T of that. Good. So let's assume that our standard matrix is A. So this let A denote the standard matrix. We stop. T just R cube to R cube. Let A denote the standard matrix of, right? Good. Of T, that. Comma, then A, so look at that, this is 3 by 3. A is a 3 by 3 matrix. So that A is what? It's a 3 by 3 matrix. A is a 3 by 3 matrix. And column K of A is T of E what? K. Okay. So the K can be 1, can be 2, can be 3, right? The K should be 1, 2, and up to 3. Okay. Let me just find a comma. K equals to 1, 2, 3. Because I did 3 by 3, right? Okay. Well, you said that the columns of the standard matrix, they are the T of E of K. Okay, so if it's a 3 by 3, then you expect that, of course, U1, T of U1, T of U2, T of U3. Full stop. So now let's go and find T of U1, T of U2, and we start. That one too has been given to us. So those one has been given to us from the question. Okay, so from the question, so you realize that T1, T of U1, this is what T of U1 has been given to us. That's what 1 is 0, 0. And he said, you claim it's equal to 1, 2, 3, isn't it? T of that. This is equal to that. T of E2. Again, T of this 0, 1, 0. This equals what? Was given to us as what? -1, 1, 1. T of E3. This 0, 0, 1. This one was given to us as 1, -2, sorry, 0. So everything was given to us. So this is T1, T2, T3, all given to us. Good. So if it's given to us, then what to be our A, our standard matrix A. The claim is what? T of E1, isn't it? Comma T of E2, comma T of what? Okay. So that we could have written the A straight away, as these are the T of U1, T of U2. So just substitute them there. So this would be symmetrics, right? T1, T of U1 is 1, 2, 3, column wise. T of U2, -1, 1, 1. T of that 1, -2, 0. That's our standard matrix. 3 by 3 matrix. Okay. So we have our standard matrix now. Once we have the standard matrix, you can use it to determine the T of what I wrote earlier. T of 3, 4, negative 5. Okay. Right. I'm supposed to give you this. But later we write it. T of x is always equals to ax for every x member of R. Because I believe R cube, right? So R cube. So this means that T of, good. So the of whatever is here is the hot value given to us. Give us what 3, 4, negative 5. Yeah, so that this should be equals to the matrix. This is the matrix, the standard matrix. That's 1, 2, 3, negative 1, 1, 1, 1, negative 2, 0, times the transpose of this. Okay. So that is okay, that would be nice. T transpose, X transpose. Okay, right. The transpose of that. The transpose that will be what? 3, 4. Because if you don't transpose it, you can't multiply. Properties of conditions for you to multiply two matrices. Right. See that the column of the first matrix, right, should be equals to what? The row of the second matrix. So if we don't do that, it will not work. Okay. Good. Don't transpose it, it will not work. So if you do that very well, that'll give us negative 6, 20, 13. Right. This 3 by 1 matrix, right? Right. This is 3 by 3. And this is what? 3 by 1. So of course, they will just give us 3 by 1 matrix. Right? That's why we have 3 by 1 matrix. Right? This is a 3 by 3 matrix. This is 3 by 1 matrix. So if you multiply the results, give us what? 3 by 1 matrix. Right? Good. So that one, let me write as a remark for you, then we close. Yes. Remark. It says this, there is a connection between linear maps and matrices. Always. Let A be an M by N matrix and let capital A, sorry, and let T of V to W be a linear transformation defined by T of X equals A of what? X, comma, for every X a member of V, comma, then T is a linear transformation. And T is what? A linear transformation. T is a linear transformation. Yeah, I can bring a transformation, yeah. So that's, yeah. But they are the same though, but then transformation makes it nice. Good.